Okay, so yesterday at the very end, we proved positive discrepancy is lower bounded by root d times n, which was tight when d was at most n to the third. And then from there onwards, we have taken a slightly different choice for our vectors, and we could only prove a lower bound of n squared over d. And I briefly mentioned that this is tight, although didn't give any evidence towards it. That it's tight for d less than d in this interval, rather, because there is a strong irregular graph with n vertices and which is d regular with d roughly n to the 3/4, and then we can take just random induced subgraphs of it, and because strongly irregular graphs have kind of very nice spectral properties, this relation between lambda 2 and positive discrepancy is actually equality for them. And then when we take random induced subgraphs, the graphs are still fairly close to regular. The lambda 2 sort of scale as you would expect them to scale, even though they are no longer exactly regular, they are close enough to regular, so you can still have similar sort of upper bounds. So you get upper bound of this form inherited for the induced subgraphs as well. So a very rough outline for this. So in particular, we can't hope to push this lower bound, which matches the one obtained for random graphs beyond n to the 2/3. Okay. Recall also that the expanded mixing lemma type of argument gives that whenever the positive discrepancy is sufficiently large constant times d, remember we have this error term of the size d in the expanded mixing lemma calculations, which is kind of needed because for complete bipartite graph lambda 2 is 0, while the positive discrepancy is linear in n. So it's not surprising that some sort of condition is required. Then lambda 2 is lower bounded by this positive discrepancy divided by n. And one should think that unless we are in a stupid regime, this is automatically satisfied. So lambda 2 is lower bounded by positive discrepancy. Also remember that the Alon Boppana type of argument, whenever the diameter of the graph is at least 4, so if d is at most some small constant times n to the 1/3, we know that lambda 2 grows like root d. But now instantly from these two observations, we get a corollary. Lambda 2 is at least square root of d or n over d whenever, so now we need g to be d regular. And here we also need g to be d regular. So whenever I'm talking about lower bounds for lambda 2, I'm always considering d regular graphs in these respective intervals. Okay, we don't really care about this in the regime where d is close to being linear, because we are now going to show how to improve this bound when d is large. So don't worry about this condition being satisfied, because we are only interested in the regime where that doesn't matter. Because if d is sublinear in n, then automatically this implies that the positive discrepancy is superlinear, so it certainly grows much faster than d. So now we are going to show how to even further improve this lower bound on lambda 2. So our theorem is going to be that if G is d-regular, and D is bounded away from half n, which something like that is a condition that we need because complete bipartite graphs have lambda 2 being 0. Then lambda 2 is lower bounded by some constant which might depend on epsilon times square root of lambda, the absolute value of lambda n, or alternatively, the size of lambda n is upper bounded by lambda 2 squared. And in particular, as the product was always proportional to D, remember this follows from Boppana's Scott. It follows that in this regime, lambda 2 grows like cube root of D. And this is tight. I'm adding hyphens here because I know examples where it's tight for D growing like n to the 3/4, which is exactly the regime where these two bounds, this bound and that bound meet. So now we could get a new theorem which states that this is true when D is between n to the 2/3 and n to the 3/4, and the last bound is true when D is in this range. Because this is precisely the breakpoint where these two curves meet. Because in both cases they give lambda 2 being roughly n to the 1/4. So this is tight. So there are tight examples when D is roughly this, when D is n over p, where p is odd prime, and perhaps many others. I think the best expert in this room to ask examples sits over here. Maybe I'm putting you in a tough position, but if you are actually interested, ask him after the class.
Yes, I can answer questions, I guess.
Yeah. Because, so a little bit about the history of this theorem. So it was first proved by Bala, Eero Raty in 26, although the preprint came out end of 2021. So here I kind of want to write down when this preprint came out, because otherwise the history will look very skewed. And his motivation came from actually from some concrete applications. So he studied equiangular lines, which is basically how many, if you give a fixed angle in n-dimensional space, how large a collection of vectors can you have? So the pairwise angle between any two vectors is this particular angle. And there he needed good bounds for lambda 2 in much denser graphs, but where Boppana bound didn't apply. And he used some very nice matrix projection arguments. It was also proved by Bernard Eeringer. I believe the preprint came out 22 and then it was published 23. Something
I
like
don't remember.
That's rough timeline. And there the motivation came from that if you view this bound as the absolute value of lambda n being of the order lambda 2 squared, then this bound is satisfied for strongly regular graphs. Basically because for strongly regular graph you have the top eigenvalue D, and then exactly two other eigenvalues, one positive and one negative. So lambda 2 and lambda n are sort of the only non-trivial eigenvalues. So their multiplicities are basically proportional to the inverses of lambda n and lambda 2, because you need a trace of the adjacency matrix to be 0. And it's there's this bound called absolute bound, which is usually written for the multiplicities of the eigenvalues, but actually translates the bound for the sizes of the eigenvalues as well. And there's a more concrete expression, which I believe is something like the number of positive negative eigenvalues that was half times the number of positives times a number of positive plus 3, or maybe I swapped the positive and negatives the other way around. But anyway, it's equivalent to this bound. So there he proved that this same sort of phenomenon occurs for regular graphs as well. And while this wasn't explicitly written, this sort of detail 1/3 wasn't, I think, explicitly written down. It's still, this bound is contained there, which is really the real core of this theorem, because all the proofs go via this intermediate step. And then, as an application of our discrepancy method, this was also proved by Sudakov, Tomon, and myself. Really, all the pretty things came out about it. All of these proofs are, to some level, have a varying degree of difficulty. They are not super long, but actually, if you look at them very carefully, so here you have some, you use some matrix projections, and this inequality is basically saying you look at the image of a certain map and compare it to the length of the image of a certain map and compare it to the length of the projection, then obviously the length of the projection must be shorter, and that gives you exactly that inequality. Here, the underlying story is very similar to the proof I'm going to show, but the details are a little bit more complicated, because a certain fact is sort of is used implicitly, so there is some interlacing applied on the tensor product of matrices to get that certain submatrix is positive semi-definite. And then a very sort of a quick yet unmotivated proof was given by Eero Raty, Sudakov, and Tomon in 2023, plus in a companion note, which is what I'm going to show now. So in order to actually prove this result, we need to introduce a little bit of more linear algebra. So matrix A is said to be, so we always talk about symmetric matrices, is positive semi-definite. If all its eigenvalues are non-negative. So basically the inner product of x and ax is always non-negative. Then the Hadamard product A circle B is the matrix whose ith entry is just the product of the ith entry of A and ith entry of B. So I guess this is the, if you ask someone who have never seen any linear algebra and ask them how would you define a matrix product, this might be what they would come up with, because they don't necessarily understand the sort of the theory behind matrices being linear operators, and that's why you want to define matrix product different way. But this is literally just a coordinate-wise product. And perhaps a little bit surprisingly, Hadamard product has some nice structural properties. if A and B are, so I use this funny greater than zero sign to mean positive semi-definite, because I'm going to use it a lot, so it's nicer if I don't have to write it down every time. Then the Hadamard products also. And one nice argument, which was implicitly used in paper Fernandinger, was that basically this Hadamard product is contained as a submatrix in the tensor product. And we know the eigenvalues of the tensor products are given by the pairwise products of the eigenvalues of A and B. And if A and B are positive semi-definite, it means that all the squarewise products are also non-negative. So by interlacing all the eigenvalues of this guy, which is a submatrix of the tensor products, has to be non-negative as well. There are perhaps more direct proof as well, but that's probably the most conceptual proof I am of. So now let's give a proof of this inequality. And this might look like it's coming out of nowhere. The reason behind it is that it's motivated by some projection arguments used by Igor, and we basically just pick the purely algebraic part of the proof to make it as quick as possible. And because I don't really have time to outline the full motivation behind the projection arguments, it's limited time. So we just pick M to be lambda 2 times I minus A. So that's a good start. We are trying to look for a matrix which is positive semi-definite. So here, and also probably a way to prove it is to prove that the VIs are still going to be eigenvalues of M. So now MVI is going to be lambda 2 minus lambda I, VI. And this guy is non-negative if I is at least 2 automatically from the fact that lambda 2 is the second largest eigenvalue. So now the only guy that's causing us problems is the top eigenvalue, lambda 1, which corresponds to the all-one vector because we are living in a case when our graph is regular. So we have to somehow make sure that that's not causing us problem. And for that one, we get lambda 2 minus d, which is heavily negative because lambda 2 is usually a little below d. So we just add p times j. And here it's convenient to view j as the tensor product of the all-one vector, which is just n times v1 tensor product with itself. Because now it's kind of, so we can always decompose adjacency matrix as lambda j times vj transpose, because these eigenvectors are orthogonal. If you haven't seen this before, I would urge to maybe spend some time in the afternoon thinking about why this is true and why in this linear algebraic arguments this actually makes a lot of sense to view it in this form. Because now basically what we are doing is that we are also using the fact that the identity matrix is just vj transpose, and this is because vj's are orthonormal basis. Because if you feed in any vector on the left-hand side and take the inner product with itself, then what you really get on the right-hand side is, like if you consider F transpose IF, then this should be just the F inner product with itself, or F1, F2. And basically we are going to get the same here on the right-hand side from the fact that features are on the basis. So that's one way of seeing why this is true. So basically what this expression is saying is that lambda 2 I minus A is this guy. All of these Vj transposes are positive semi-definite matrices, and we want to add something that is makes this whole sum positive semi-definite. Now the only problem is the j equals 1 term, so we just add a suitable multiple of V1 transpose that makes the j equals 1 term also non-negative. Here I have chosen slightly too large constant, so what you could do here is just plugging alpha j over here, solve for alpha so that the m times the over vector gets killed. But for the remainder of the calculations, the correct alpha is going to be the same as p up to lower order terms. So especially if we scale everything. So you should really think of this more as not a p, but p times n, and this j as V1 transpose, and then it's the correct constant up to a lower order terms, p times n, which is much larger than the lambda 2 in general, or in the regime we are interested. But this just makes our calculations a little bit more simpler, so I'm just gonna use that one instead. So, as already said, then mvi equals mu I vi for some mu I greater than equal to 0 for I. So it follows that m is positive semi-definite. So let X be the Hadamard product of M with itself. So now we just have to figure out what various different Hadamard products of this matrix are. So the Hadamard product of I and A is 0, as A has only zeros on the diagonal. The Hadamard product of I and J is just I. In fact, the Hadamard product of X and J is just X for X, because J is the Alon matrix. So now we get what A times the Hadamard product of A and G is. Also, because we are working with 0, 1 matrices, we have this nice relation, the Hadamard product of each with itself is just the original matrix. So the point is here is that when we take this Hadamard product, what we are left with is going to be expressible as a linear combination of I, A, and J. So if we think of M living in the space of matrices whose basis is given by I, A, and J, then the Hadamard product of M with itself also lives in the same space. So in particular, X is going to have the same set of eigenvectors as M, which is and with A, which is going to be a very convenient thing for us because we know that all the eigenvalues of X has to be non-negative by our exercise / fact. But we also know what the eigenvectors are, so we can just see if those two combinations together give us any information, because we know that all the eigenvalues must be non-negative, but we can also just plug in an eigenvector and see what eigenvalue it gives to us and see if we can deduce anything nice from it. Okay, so let's see what this actually is. So we get lambda squared times I plus A plus B squared J. So here is the sort of the A squared B squared C squared terms, so to speak. Then we have another product for I and A, which is 0, so that term doesn't contribute at all. Then A and Pj, so here we get minus 2p, the Hadamard product of A and J, which is just A, and then plus 2p lambda 2 I, which is just Hadamard product of I and J. So if we collect the terms, what we get is this. So here we start seeing why p equals half is a very important point, because that's where the sign of this middle term flips from positive to negative. So now if we feed in anything else than v1, then obviously this term doesn't contribute, because j times vi is 0 for every I greater than or equal to 2, because every other eigenvector is orthogonal to Alon vector. So remember, j times vi is 0 for all I greater than 2, as v1 is the Alon vector, and vi in a product with v1 is 0 for all I greater than 2. So this term doesn't matter. So writing XVI equals mu I vi for I greater than or equal to 2, then what we get is that mu I is just going to be lambda 2 squared plus 2p lambda 2, because I times vi is just going to be vi for every I, plus 1 minus 2p times lambda I, because AVI is going to be vi. And we know that this has to be 0 as x is positive semi-definite. But this at least 2 epsilon, so in particle a positive constant. And this is, well, let's, for simplicity, suppose that we are in a case when lambda 2 is sort of moderately large, so not a small constant, then this is clearly, roughly speaking, lambda 2 squared. So this is lambda 2 squared and positive. This is 2 epsilon times lambda I, and it has to be always not negative. So when is this hardest to satisfy? Obviously, when we pick this to be as negative as possible, so negative and large by absolute value. So when we pick I equals n. So I equals n gives us sort of most information. It gives us the absolute value of this term has to be at least as large as the absolute value of this term, because this is positive, and yeah, this is certainly negative term. So this has, and by interlacing, this has to be positive. So this has to be large and positive, and that has to be, well, at most the size of this. So what we get is lambda 2 squared plus 2p lambda 2 has to be at least 2 epsilon times the absolute value of lambda n. So we get our results. And as I said, this is not it's a nice and short proof, but it's not the best proof of this fact because it's really hard to motivate where this is coming from. And this is not the end. So Chang proved, but this is sort of basically the same things that we discussed when I mentioned that there was this breakthrough, the Alon Shudakov conjecture, where you get the uniform exponent. So these problems are closely related to each other. So one of the places where this technique applies is that if Chang proved that if our graph is far away from the wrong graph, so this means that if we cannot achieve our G by changing the status of epsilon prime n squared edges or non-edges, starting from the wrong graph, then lambda 2 of G grows at least as large as 1/4 minus epsilon. And this 1/4 is the best possible in the sense that there are examples for certain densities, linear densities, where n to the 1/4 is the correct value or correct exponent for lambda 2. So here I'm treating the complete graph and empty graph as two wrong graphs. So this variant of the result addresses only graphs with sort of constant edge density. Obviously, it doesn't really matter because the sparse graphs are already addressed by those theorems, and very dense graphs are sort of little o n squared close to the complete graph, which we treat as a two-wrong graph. So in that sense, we can just restrict our attention to this regime. There's also a variant of this result where one only assumes that you are polynomially away from a two-wrong graph. So this n squared is replaced by n to the alpha for alpha less than 2. And then you get bounds here where the exponent is not quite 1/4, but I believe 1/6. So you lose a little bit of the constant, but actually can get much stronger results. So there's this strong stability in the sense. So basically this result proves that while we have these special cases, two-wrong graphs, where lambda 2s are very small, these are really, in some sense, the only cases where lambda 2 is small. And in all the other instances, we have a lower bound for lambda 2. And here, as always, I'm assuming G is irregular. Actually, he proved his results for the complementary scenario. So if he considers, like, if you have a irregular graph, then its complement is d and n minus 1 minus d irregular. And it's not too hard to see that the spectral, the other lambda 2 up to lambda n are closely related in a sense that you just negate your eigenvalue. So lambda 2 of G corresponds to lambda n of G complement. And when we consider lambda n instead, now we actually have much more freedom. So they are not this 2-bit example showing that lambda 2 can be 0 for all densities to complete multipartite graphs. But actually, there you have the corresponding obstructions are cliques. So he actually proved that if lambda n is small, so much smaller than n to the by absolute value, meaning by absolute value much smaller than n to the 1/4, then G has to be union of or close to a union of cliques. And there you don't have to add in the assumption that the cliques are equal. So in some sense, it's a little bit more general than what I said results. But morally, this is kind of like has most of the features that the main result also has. Okay. So in some sense, finally we were able to push us beyond the. So for positive discrepancy, the trivial lower bound was linear, which kind of corresponds to saying that lambda 2 is at least a constant. Not quite because we have this plus d terms, but for when d is alpha and for very small alpha, then we would get some constant lower bound for lambda 2, which is not really great. We now managed to push far beyond it. So the question is that can we similarly push beyond the n squared over d bound for the positive discrepancy? Turns out that one can. And d is again less than strictly less than half. Then the positive discrepancy is lower bounded by is the 1/4 times n after a log factor. So in the range when d is alpha n for alpha small enough, this gives roughly an exponent n to the 5/4. So we beat the linear bound. And not surprisingly, this sort of framework of Zhang. And I should also mention there was this follow-up paper by Chen Yin, Alex Milosevic, this one, Toman, and Shengtong Chang. So, which basically says that if G is far away from the theorem graph, then we can then we can beat the linear bound for some uniform delta, depending on epsilon prime. So, for the last 50 minutes, I will not prove this exact bound, but I will give a slightly easier proof, which has the same ideas with a lot of technicalities removed. Okay, it has many same ideas, but it's missing one crucial step, which gives us a bound which still beats the linear bound, but doesn't match quite the exponent n to the 5/4. So what I'm going to show instead is a lower bound of the form. I believe what comes out at the end is 1/7 when d is alpha and for alpha instead of alpha is epsilon and bounded away from 0. And this is going to be, so there are going to be two important steps. So one of them is that we now formalize a little bit more the semi-definite relaxation of the positive discrepancy, because now we are basically using the same heuristic idea behind the Goemans Williamson method, but instead of actually picking the vectors xu explicitly, we use the spectral properties of A to determine it. In particle, we have no idea what they look like. We just know that they exist. So in particle, it's a problem because we don't know at all how large those inner products are going to be. So in particle, we can't sort of really look at the positive terms and negative terms and do this estimates carefully on both of those sums to ensure that their difference is still large. Because we just have a bound on their difference, but we don't know if that difference is actually much smaller than the absolute, the sort of, because, okay, so we have a terms of the, so in this approximate version of the Goemans-Williamson bound, we have these two terms. Or rather, the situation is even more trickier because we should split in this into positive and negative, and this also into positive and negative. And then we could put these two together because they are sort of the ones where if we move this minus sign inside, the contribution is going to be positive, so we kind of need a bounds for them and those two together. But now the problem is that maybe this is somewhat large, but within each of these groups, the sums are even larger. Now, when we add them together with the signs, it could be that the sum is still large, but it's coming from some sort of a rounding error, which is small compared to these sums. So in particle, if we use any sort of estimates that, okay, we lower bound the original sums in this arcsine expressions by 0.99 times this sum, and then we subtract fully this sum because if the inequalities work that way, then all of a sudden we have the estimate is a disaster because then we have a bound which is proportional to this much larger sum because the whole sum is somewhat large, but the individual signed components can be even larger, which wasn't the case in the example when we chose the vectors correctly, because there the terms, all these inner products were non-negative. So this sum really consists of all the positive sums, and we knew that all the contribution came from this guy. So even if we did a slightly suboptimal rounding error, it didn't matter because this was little o 1 times that one, or a very small controllable constant times that one. But that may not be the case when we choose these vectors in an abstract way. So what I'm trying to say is that this heuristic we had yesterday no longer applies when you don't know anything about these vectors. So that was kind of like a very bad way of doing things, but kind of by a fluke work with that instance. So, but there is fortunately a way to do it formally, and that's something called graph index inequality. So I'll just make sure I write. So growth index inequality is something that's quite sort of well known in functional analysis and was proved many decades ago. So there's a graph variant proved by Alon, Makaryshev, another Makaryshev, and Naur, 2006, which says that if G is a graph with no loops, and A is a matrix, let's say for our purposes there is symmetric weight. No, I think it doesn't matter, but then actually I want to call this B because we are going to apply it to something that involves adjacency matrix, so that would be way too chaotic. So if I take the weighted sum of these xi, terms, so know that because G is a graph with no loops, I'm not having xi squared terms. It's only this cross product, which is, as we remember, max cut can be written in this form. So not surprisingly, positive discrepancy can also be defined as optimization problem in this form. Then this is at least as large as some constant depending only on G times the supremum or the semi-definite relaxation of this problem.
Do you have any control for S1 to Sn? For this supreme, do you have any control S1 to Sn? Otherwise,
Yes, sorry. Thank you. So because we have points in the sphere, we want the corresponding sort of one-dimensional condition here. So they are between -1 and 1. So if G is the complete graph, then this CG is going to be 1 over log n. And applying this to matrix B, which is chosen to be the adjacency matrix minus P times the over matrix, we conclude that the positive discrepancy is lower bounded by some constant divided by log n times the sub minus this sum. Because if you think about it, the positive discrepancy is just the max of xi's being between -1 and 1 of some aij minus p times xij. Sorry. Here I should really have them between 0 and 1 because for the same reason that positive discrepancy is over this binary set 0 and 1, where we assign each thing to be either in the set or outside the set. And now this first term is counting the number of edges, aij, xi, xj is indicated function of both I and j being in our set U, and p times xi, xj is counting the expectation of u choose 2. But it's not too hard to conclude that this is some small constant times, moderate size constant, I think something like 1/4 times this guy. basically coming from the fact that if this is large, then it's not too hard to show that either the optimum is set n at -1 or 1, then you can prove that either the set A, which corresponds to 1s, or the set B corresponding to -1s, have large discrepancy, because this is basically the discrepancy of A minus the discrepancy between A and B plus discrepancy of B. And you also know the discrepancy of A plus discrepancy of A and between A and B plus discrepancy of B is 0. Because it's the discrepancy of A union B, which is the discrepancy of the full graph. So you know that twice times the discrepancy of A plus twice the discrepancy of B is large. So it's this guy. So at least one of A or B, namely at least one of the sets which corresponds to the 1 entries or the -1 entries have large positive discrepancy. Again, this is one of those things that if you really want to learn this properly, play around with these facts so that you get some sort of a intuitive idea how these equations with sets and their complements and discrepancies work out. Yes.
Here, G sometimes G as a clique is an auxiliary graph and A is an adjacency of the other graph.
Yes, sorry, that's a good point. So I used G for two things, which was maybe very confusing. So if H is the clique, then the growth index constant for the clique is proportional to 1 over n. So we apply graph growth index inequality for Kn. So we really want all the terms to be there. Maybe I should have stated this graph growth index inequality just for the clique, but it's a bit more general. And for example, for bipartite graphs, the growth index constant is actually it's really a constant independent of n. So that's why it's fairly nice in a sense that sometimes you actually get semi-definite relaxations where you only do some multiplication with constant rather than something that decays to 0 in n.
But I had the same question also. Why are we applying for Kn there?
Sorry? It's because here we are summing over the edges of H. So the positive discrepancy of G is the sum over all I not equal to J of Aij minus P plus Xij. So this I can write positive discrepancy as this optimization problem. And here I'm really summing over all I not equal to J, which is same as saying for all Ij in Kn. Up to maybe factor of 2, because here we have ordered pairs, here we have unordered pairs. But it's fine because the matrix is symmetric. So this is this is our lower bound for discrepancy. And now if we apply the growth index inequality for the graph Kn, namely here we are summing of the edges of G, or let's call this H instead. Because we want to sum over all the pairs I not equal to J, we have to apply the growth index inequality for H being Kn. And then we get the same summing over for I not equal to J times the same expression, but now we replace the Xij with the inner products. And we lose a 1 over log n factor. So if you got slightly lost with the details, don't worry, because what we really want to use here.
So is it always when we apply, we use for the complete graph?
Sorry?
We use the...
Yeah, we always apply it for the complete graph. So, okay. So, given this vectors v1 up to bn, let X be the matrix where Xij is at the inner product of Pi Bj. So then, a fact, then X is positive semi-definite.
Sorry, that was not the quality use. So should every graph be G or H?
Every graph should be H.
Every
Yes, because here I changed it to H because just to ensure that we don't, because we use G in this application. So, I mean, like originally, if you wrote this in terms of G, that's fine, because here we didn't have any host graph G we were considering. This is purely a graph theoretic inequality where we have only one input graph. You can call it whatever you want to. But for the clarity over there, because we usually use G as our graph that we are considering, it might be easier to sort of denote H as the graph we are applying the Goemans inequality over, and that's going to be always the complete graph because we want to basically we are summing over all the distinct I and J, which is the same as summing over all the edges of complete graph. So, given vectors v1 up to vn, define a matrix xij whose ijth entry is the inner product of vi and bj. Then X is a symmetric matrix, obviously, and I claim that X is positive semi-definite. I'll leave it as an exercise, but it's also easy to check that the converse is true, and it's a little bit more convenient to work with positive semi-definite matrices instead. So it's useful to know that these are actually in correspondence. So if you have a positive semi-definite matrix, which is hence symmetric, then there exists vectors v1 up to vj, so that xij is the inner product between vi and bj. And if you want to prove it, one way to do it is to just look at the LU factorization of x and work your way from there. So define given G and hence the adjacency matrix A, we define the relaxed semi-definite relaxation of the discrepancy now for X, which is okay. And note that if we have some condition on the diagonal entries, then the same condition is equal to the for the norm of BIVJs. So here, if we have vectors on the sphere, then it corresponds to xii being equal to 1. Also, it's actually easy to see that in the Goemans inequality we could relax ourselves a little bit, and instead of taking vectors from the sphere, we can take vectors from on the unit sphere. We could just take anything that's inside the unit sphere, because the maximum is clearly attained when we scale the vectors to unit sphere for the same reason as always in our optimization problems, considering the interval from -1 to 1 is the same as considering discrete points at -1 and 1. Because here as well, we don't have the diagonal term, so scaling some vi by a positive constant or negative constant is just going to change this function in a linear fashion. So hence it's always best to pick the constant to be as large as possible, subject to the condition that they are at most unit vectors. So here we take X to be positive semi-definite matrix so that the diagonal entries are at most 1. So let this be the inner product between X and A minus Pj, so the Frobenius inner product, where the Frobenius inner product of two matrices is just trace of A transpose B, which is just sum over all I and J of Aij, Bij. So note that what we have here is basically the start discrepancy of x, apart from there we include the diagonal for convenience, whereas here we don't. But that's not a big of a difference, because the diagonal entries of xii are bounded above by 1. So when we sum them together, multiply by b, and take the minus of that, we get something which is between 0 and minus d, which is going to be linear. So if we try to prove superlinear bounds, and especially something that is not n log n, but rather n to the 1 plus delta, then bounds for disk star are going to give us bound for the positive discrepancy. So again, additive minus d terms don't matter. So define the positive relaxed discrepancy to be the that's again right supremum for the sake of clarity. So then morally, the relaxed positive discrepancy is at least as large as positive discrepancy. Here we have to take some we have to sacrifice some multiplicative constant and maybe this additive d term, which should be interpreted as not interesting things. And where does multiplicative constant come from? It comes from the fact that here, for the positive discrepancy, we should really pick these numbers to be between 0 and 1, but here we want to relax them to be between -1 and 1. Now, this basically corresponds to choosing these vectors, which gives you the matrix from a one-dimensional subspace instead, which corresponds to just having real numbers between -1 and 1 rather than n-dimensional vectors. And this lower bound follows from Grothendieck's inequality. So, morally, and how you should view this. So up to multiplicative constants.
So where is the d from?
The d comes from the diagonal. So remember, here we don't have the diagonal entries. Here in the Frobenius inner product, we take the diagonal entries. So this is coming from the p times xi, sum of the xi's. But we know that because xi's are almost 1, that contributes something between 0 and -d. So I think in one of those bounds, probably here, I don't think we actually get it, but just to be on the safe side, I just keep adding this plus d and minus d. So they are, but really how you should view this is that there is this sort of the positive discrepancy is upper bounded by the relaxation and lower bounded by the relaxation divided by log n. So far, it's not at all obvious why do we care about these things. I'll get in a second. So similarly defined. We can define the negative discrepancy and it satisfies the same properties. So now we have an analog of Pulver Scott. That their product is grows at least d times n squared whenever d is between, let's say, 1 and n over 2. So here I'm ignoring the fact of 1 minus p because for p less than half, 1 minus p is at least half, so we can embed it in the multiplicative constant, and the p times p terms together with one of the n's gives us d. Okay, but so far this is not leading anywhere. Because we still have an upper bound of d times n for both these positive and negative relaxations. So we get only a linear lower bound. But we proved that actually for these relaxations, there is a positive dependence between them. So I'll just state it informally at this stage, but this is just how to motivate what's coming up next. So up to error terms, which don't matter in the regimes we are applying it. So if lambda 2 is not too large, then we get a positive dependence between the positive and negative discrepancies. And if lambda 2 is large, then the positive discrepancy is also large. So basically now we are in a situation where, roughly speaking, if lambda 2 is large, so think now of the regime when d is n. And we are aiming for bounds which are beat the linear lower bound. So this guy is saying if lambda 2 is n to the 1 n to the 2/3 plus delta, then we are good. Because and think of d being proportional to n. Because then what we get here is n squared plus 3 delta divided by n. So we get n to the 1 plus 3 delta. Okay, so assume that's not the case. So lambda 2 is small-ish. Then we get that the positive discrepancy is lower bounded by n cubed divided by the negative discrepancy. So we get a proper improvement as long as the negative discrepancy is not larger than n to the 2 minus delta. But if the negative discrepancy is at least n to the 2 minus delta, then this guy gives us a bound of the form n to the 2 minus delta divided by n to the 2 thirds plus delta, which gives us a bound of the form n to the 4 thirds minus 2 delta. But for delta small enough, that's going to be greater than 1. So if we can prove all of these three statements, then we get a bound of the form n to the 1 plus delta prime for some small delta prime. And by doing actually this optimization properly, we can work out the constant, and it's going to be n to the 8 over 7, which is going to be the bound. And also we get an improvement for d sufficiently close to n. But really this d roughly being n regime is the kind of the model we are interested in. So that's sort of a short teaser what's going to come ahead. So this part over here is actually a special case of a little bit more general bound. So we claim that the positive eigenvalues and their moments are lower bound the relaxed discrepancy. So okay, so let K be let capital K be chosen so that the positive eigenvalues are the first K. And in the first instance, we pick X to be this matrix. So X is positive semi-definite, as each of these VI transposes. Then we have to verify that XII, so the diagonal entries are less than 1. Well, if we take the O1 matrix and subtract X, this is going to be V1 transpose plus this, and this is going to be a positive semi-definite as well. So this means in particular that the diagonal entries of I minus X has to be non-negative, because this holds for all the positive semi-definite matrices. And why is this? Because EI transpose BEI is just BII, and this has to be 0, at least non-negative, whenever B is positive semi-definite. So from here we conclude XII is less than 1. And it's an exercise to show that discrepancy of X gives you the sum of the first eigenvalues. For the third one, we choose x to be 1 over d times lambda squared bi transpose, which is clearly positive semi-definite because each of these is positive semi-definite, and we are multiplying them by non-negative numbers. And now 1 over d times a squared minus x is positive semi-definite for similar reasons, and the diagonal entries so what I forgot to say that let's assume that G is linear regular. I'm only going to show the sketch under the assumption that the graph is regular, which is a very crucial thing I forgot to say. All these details work out for non-regular graphs with much more complicated details. But yeah, it turns out to be a little bit, especially in the next step, we are going to show that to assume that the graph is regular. So now for regular graphs, a squared ii is just the sum of aij hai, which is basically the sum of the neighbors of I. And it's because G is linear regular. And this gives the bound. And the rest is an exercise. How do you... I hope I wrote this correctly, but basically you apply Cauchy-Schwarz inequality to the first and second bound. The first and third bound to get the middle, to get the last one. So in particular, the middle bound implies that positive discrepancy is lower bounded by lambda 2 cubed divided by d. Okay, so now we want this final lemma, which basically proves that if you have a large negative discrepancy, we can flip it to a large positive discrepancy. So let's suppose that X is a positive semi-definite matrix. All the diagonal entries are less than 1, and X is orthogonal to J under the Frobenius product. What does it mean? It just means that the sum of the entries in X are 0. So basically, if we think about X as the sort of the weights put on the edges of our graph, edges on all the pairs ij, it means that the sum of the weights are non-zero. Then the discrepancy of X is just going to be the inner product between F less than A. So this is basically we are asking, if we want to maximize the discrepancy, we are asking, how could we find a positive semi-definite matrix where the sum of the entries is 0? So basically the weight is sort of it doesn't have a bias towards positive or negative numbers. This PJ is basically just saying that we sort of blend the average to 0. Because that's always possible to attain by adding a suitable multiple of j to x. Maybe by sacrificing this constant that all the diagonal terms are less than 1, but only sacrificing it up to multiplicative constant, so it doesn't really matter. So what we are asking, can we find a positive semi-definite matrix X so that the weights put on it sum up to 0, but they have a heavy bias towards the edges of G? If we don't, then we know by Boppana's code that we have a large negative discrepancy, which means that there is a positive semi-definite matrix X, so that the weights put on the edges of G have a large negative bias. So now the question is that can we somehow, from X, cook up a matrix Y so that we flip the bias from negative to positive? So idea, consider the discrepancy of X Hadamard product minus A. This would be great because all it's basically saying is that we flip the and then we subtract all the sort of enough stuff so that the weight sum up to 0. This would be great because it flips the heavily negative bias on the edges of G to a positive bias. But the problem is that this is not necessarily positive semi-definite matrix, because we only know that the Hadamard product of positive semi-definite matrix is guaranteed to be positive semi-definite. Okay. So let's make it positive semi-definite. So what if we consider, so here, let us suppose that disk of X is heavily negative. So let's consider Y, which is the Hadamard product of X. Minus this guy. Where this guy is positive semi-definite, because we have seen this before, or a rather scaled version of it. Sorry, here I should have a E over lambda 2. Because we saw lambda 2 times this matrix as our M when we proved that lambda 2 has to be always at least constant times cube root of D. And what is this basically saying? It's basically we are adding, so X Hadamard product with I does very little. It's just a diagonal matrix with entries xii, so the contribution of that term is going to be very small. The Hadamard product with X and minus A is really the thing we want to. But in order to make this matrix positive semi-definite, and ensure that the diagonal entries are less than 1, that's why we divide by lambda 2, we have to scale this down by lambda 2. Which motivates the 1 over lambda 2 factor in the positive relation between positive and negative discrepancy. And then we have to add this correction term to ensure that we get the proper contribution from V1 as well. Because now, otherwise the eigenvalue corresponding to V1 of this matrix is going to be 1 minus D over lambda 2, which is way too large. So we have to add back something that is ensures that V1 also has a positive, non-negative eigenvalue. So the lemma we are about to prove is that if if xj f is 0, it's not really needed, but it's added here just for the sake of making the calculations easier. Then the discrepancy of y is minus b times the diagonal and sum of the diagonal entries minus 1 over lambda 2 times the discrepancy of x. So then we pick discrepancy of x to be the negative relaxed discrepancy, and we conclude that the positive relaxed discrepancy is at least the discrepancy of y, because y is positive semi-definite, and that's at least, so here I should have minus sign, and that's at least the negative relaxed discrepancy. So basically, this statement easily implies the positive relation between the positive relaxed discrepancy and the negative relaxed discrepancy. So in order to prove a blower bound properly beating the linear bound when p is less than half minus epsilon, all we need to show is that this statement is true. So recall that y is I minus 1 over lambda 2 a plus alpha j, pj, p divided by lambda 2j. And y is positive semi-definite as y vi is mu I vi, where mu I is 1 minus lambda by lambda 2, which is non-negative for I greater than 2, and mu 1 is 1 minus d over lambda 2 plus bn over lambda 2, which is nearly none. Okay, yi is 1 plus p divided by lambda 2. That's a bit annoying because it's actually greater than 2, greater than 1. But this is at most 2 by about lambda 2 greater than 1. Remember, lambda 2 is proportional to d to the 1/3 in this regime. So basically, if we really want to be pedant, we replace y by 1 over 2 times y. But that's only going to matter the constant factors. So let me not add factor half in front. Okay, so what's the discrepancy of the Hadamard product of y and x? So discrepancy is the Frobenius inner product, so it's just linear. So we get the following expression. Okay, so I made a small mistake here. So I obviously need some condition on the density because this theorem should break down at half. So yes, this is minus a constant divided by lambda 2 times discrepancy, but the constant is actually 1 minus 2p. So, but that will anyway come from the proof eventually. So the Hadamard product of I and x is just going to be the diagonal matrix with entries xii, and we take the inner product with a minus pj, whose diagonal entries are going to be minus p's because a has zeros on the diagonal. So the first term is going to give us minus p times the sum of the xi's, which is what we have over here. So now we just have to verify that the rest is what we claim it is. So I claim that if I have a Frobenius inner product of A Hadamard product of B and C, then I can switch the Hadamard product to the other side. Why is it? Because this is just sum of over all I and j of xij, yij. And ijth entry of the Hadamard product is just the product of the ijth entries. So basically, it doesn't matter where the Hadamard product here is lying on which side, because we are taking the product of the ijth entries, and the Hadamard product is just the product of the ijth entries. So, I mean, both of these guys is just going to be aij, bij, cij, and some overall, both of them. So that's fine. So we apply this observation here in the second term. So this is going to be 1 minus lambda 2 times. So we switch a to the other side. So the Hadamard product of A with itself is A, because it's the 0, 1 matrix. And then the second term is going to be minus B times A. But this is just the discrepancy of x as x was orthogonal to J. So we are done. If we didn't have the assumption that x is orthogonal to J, then we have to do a little bit more calculations. But as I said, that's not really a restrictive assumption either, because if you sacrifice your condition xii less than 1 to xii less than, say, 2, then you can always add a suitable multiple of J to it, for which the multiple is bounded by absolute value by 1. So then x plus this alpha j has its diagonal entries bounded by at most 2 by its absolute value. So then if you scale it down, you lose a little bit by from the discrepancy. And the discrepancy of x and the discrepancy of x plus alpha j are always the same, because a minus bj its inner product with j is 0, basically because all the other eigenvectors are orthogonal to B1. Okay, so this proves that there is a linear, positive relation between the positive and negative, positive discrepancy and the negative discrepancy. And as I briefly sketched, those three bounds, the Boppana analog, this one, and the positive discrepancy is lower bounded by the cube of lambda 2 divided by d. When you combine all three together, you get the improvement for the linear bound. Because I'm already running over time, I think I'll not write it down. It will be in the notes, and if you work out the details, you can also get a good exponent. So I guess that's a good time to stop. Thanks for attending, and if you have any questions, I'm happy to answer them now or later.